Imagine you hired a brilliant software engineer, gave them a massive code base with hundreds of thousands of lines of code, and asked them to fix a bug. They confidently walk into the right room of the building. They even open the right filing cabinet. But then they pull out the wrong drawer, skim past the exact pages that contain the answer, and somehow still manage to write a patch. Sometimes it works, sometimes it does not, and you have no idea which part of the process actually went wrong. That is essentially the situation we are in right now with the best AI coding agents in the world. And a new piece of research has finally built the tool to expose it.
Okay, so I use AI coding tools, and when they fix something, they either fix it or they do not. Why does it matter which internal step failed? A bug resolved is a bug resolved, right?
That is exactly the mindset that this research is pushing back against, and honestly, it is a really important point. The existing way we evaluate AI coding agents is a simple pass or fail. Did the agent resolve the issue? Yes or no? And that binary score is useful, but it is hiding something critical. There are actually two completely different ways an agent can fail. Either it cannot find the relevant code in the first place, or it finds the right code but cannot write the correct fix. These are completely different problems that require completely different solutions. And right now, when an agent fails, we have no idea which one of those two things went wrong.
So the problem is that the scorecard is too simple. It is like grading a student by whether they passed the final exam, but never looking at their homework to understand where their understanding broke down.
That is a perfect analogy. And what this new benchmark called SWE-Explore does is essentially create that homework grade. It isolates just the first part of the process, which is the exploration step, the moment when an agent reads through a repository and decides which parts of the code are relevant to the issue it needs to fix. SWE-Explore asks a very specific and measurable question. Given a bug report and a repository, can the agent find the right lines of code before it even tries to write a fix? And here is the surprising part. When you measure this in isolation, the results are quite sobering.
Before you get into the results, walk me through how you even measure something like that. How do you know which lines of code are the right ones? Someone has to decide that in advance.
This is actually one of the cleverest parts of the research, and it sidesteps a really hard problem. Manually annotating the correct lines for hundreds of issues across 10 programming languages and over 200 repositories would take forever and be incredibly inconsistent. Different human annotators would draw different boundaries. So instead, the researchers use something they call trajectory-grounded supervision. Here is how it works. They took real, successful AI coding agents, agents that actually solved the issues, and they recorded exactly which lines of code those agents read during their successful repair sessions. The idea is that if multiple independent agents, using different approaches, all consulted the same specific lines while successfully fixing the same bug, those lines are almost certainly the important ones. Think of it like asking several detectives who all independently solved the same case which clues they used. The clues that every detective visited are probably the key evidence.
I actually like that, but let me push on it. Is the code that a successful agent happened to read really the same as the code that was necessary to read? An agent might read a lot of unnecessary stuff on the way to a fix, and you would still label all of that as important.
You are absolutely right to challenge that, and the researchers anticipated exactly this concern. They did not just take the union of everything every agent read. They took the intersection, meaning only the lines that appeared across multiple independent successful runs from different model families. Then on top of that, they did an additional refinement step using another AI model to check whether borderline regions were actually load-bearing for the fix. And finally, human reviewers manually audited every single promoted region. So there is a layered quality control process. It is still an approximation of the truth, and the researchers acknowledge that clearly in the paper, but it is a very principled and carefully validated one.
Okay, fair enough. So they built this benchmark with 848 issues across 10 languages. What did they actually find when they ran the top AI systems through it?
This is where things get genuinely interesting. The headline finding is that modern AI coding agents are actually quite good at finding the right file in a repository. What the researchers call file-level hit rate is strong across all the major systems. So agents like Claude Code, OpenHands, Codex, and several others are reaching the correct file the majority of the time. But then you zoom in to the line level, and the picture changes dramatically. These same agents are only covering about 14 to 19% of the specific lines that successful solutions actually relied on. They are getting to the right room, but they are missing most of the actual evidence inside it.
Wait, so they find the right file more than half the time, but they only cover like 15% of the relevant lines? That gap is enormous. How is that even possible?
Think of it this way. Imagine a debugging issue that involves a subtle overflow bug in a function that is 80 lines long, buried in a file that is 730 lines long. The agent finds the file. It even opens it and reads some portions. But it reads the wrong portions, or it reads a 30-line window around the function instead of the specific 20-line span that contains the actual bug and the relevant test case in a completely separate file. Finding the file is a core signal. Covering the precise lines that the fix actually depends on is a much finer and much harder challenge. And the research shows that essentially all current agents are stuck at the coarser level.
So what about the older, simpler approaches, like basic keyword search, the kind of thing that was used before large language models? How do those compare?
Here is one of the most striking results in the paper. Classical retrieval methods, things like BM25 and TF-IDF, which are essentially keyword matching systems, perform almost identically to random chance on this task. On file-level hit rate, BM25 scores about 0.079 and TF-IDF scores about 0.14, compared to essentially 0 for random. Even a modern dense retrieval approach, which uses neural embeddings to find semantically similar code, barely does better. The agentic systems, the ones that actually interact with the repository, read files, follow references, and reason about the code, are a completely different tier. This confirms something important. Repository exploration is not a search problem. You cannot just match keywords or embeddings and find what you need. You have to actually reason about the code interactively.
All right, I want to get skeptical here for a minute. Because the whole premise of this benchmark depends on the idea that better exploration actually leads to better bug fixing. But is there real evidence for that, or is this just an assumption baked into the design?
This is one of the strongest parts of the research, and they went a real effort to demonstrate it rather than assume it. They ran a controlled validation experiment. They took each agent's top 5 recommended code regions, hid everything else in the repository from the patching agent, and then measured whether the restricted context patch actually passed the test suite. And the correlation between their exploration metrics and downstream bug fix success rate is remarkably high. Context efficiency, meaning how much of what the agent selected was actually relevant, has a Pearson correlation of 0.95 with downstream resolve rate. That is an extremely strong relationship. The research is not just measuring exploration in a vacuum. It is showing that exploration quality is a direct driver of fixing success.
0.95 is almost a perfect correlation, but Pearson correlation can be misleading. What about rank correlation, which is more robust to outliers? Because a couple of extreme data points could inflate that number.
You are doing exactly the right thing to check that. The Spearman rank correlation for context efficiency is 0.739, which is much lower than the Pearson value. The researchers actually discuss this openly. The rank-aware metrics like NDCG, which measures how well useful evidence is ranked early, show very high Pearson correlations but weaker Spearman correlations. What that means is these metrics are excellent at separating broad quality tiers from each other, like distinguishing classical retrieval from agentic exploration, but they are less reliable for ordering two very similar systems that are close together in performance. The researchers explicitly recommend reporting a mix of metrics rather than relying on any single score, which is the honest and rigorous thing to do.
Okay, so let me get this straight. The benchmark shows agents find files okay, but miss lines badly, and better exploration actually does lead to better fixing. But here is my practical question. Does it matter whether the agent includes too much irrelevant code, or is missing key code the bigger problem?
They ran a really elegant experiment to answer exactly this question. They took the perfect set of relevant code regions and then systematically degraded it in two ways. In the first condition, they progressively removed core regions, giving the agent less and less of the important evidence. In the second condition, they kept the same budget of code, but replaced the removed core regions with random, irrelevant code from the repository. The result is very clear. Missing core evidence is the dominant failure mode. The resolve rate drops sharply as you remove key code, but once you have most of the core evidence present, adding irrelevant noise does not hurt very much. Modern patching agents are pretty tolerant of extra irrelevant code as long as the essential pieces are there. The implication is that the field should be focused on improving recall, meaning making sure agents find all the important lines, more than improving precision, meaning filtering out noise.
There is also something interesting you mentioned about what happens with an empty context baseline. If you give the agent no repository code at all, sometimes it does surprisingly well.
Yes, and this is a genuinely important caveat for the field. On the easier subset of issues, there is a small dip in performance when you give the agent a tiny incomplete slice of the correct code, compared to giving it no code at all. A plausible explanation is memorization. The AI model may have seen these popular repositories during training and can sometimes guess the fix from the issue description alone, without needing any code context. But when you give it a small, incomplete slice of context, it tries to reconcile that partial evidence and gets confused. This means that benchmarks using well-known repositories could be reporting inflated results, and the community should be careful about interpreting zero-context baselines as evidence of true reasoning ability.
What about the specialized academic localization agents? The ones specifically designed to find bugs, not just general coding assistants. Do they actually do better at the exploration task?
The results here are surprisingly nuanced. The academic localization agents do not uniformly beat the general-purpose coding agents. Autocode Rover, for example, is very precise when it does identify something, but it is extremely conservative and misses a lot of relevant code. Orcaloca has almost no noise, but also misses most of the relevant regions. Lock Agent performs very similarly to general coding agents despite being specifically designed for localization. The one academic agent that genuinely stands out is CoSIL, which achieves by far the highest line-level recall of any non-Oracle system. It uses an iterative code graph search approach, following the relationships between code components rather than just doing one-shot search. This suggests that the key to better exploration might be this kind of iterative, relationship-aware search, rather than just using a more powerful base language model.
So replacing the brain inside the agent with a smarter model does not solve the problem. It is the strategy that matters more than the raw intelligence.
Exactly right, and the paper has a really compelling experiment to show this. They ran the same mini SWE agent framework with 6 different underlying language models, ranging from GPT-5.4 down to Gemini 3 Pro and GLM-4.7. Across all of them, the same bottleneck appears. File-level hit rates are much higher than line-level recall. The stronger models do a bit better, but none of them escape the fundamental pattern. Swapping in a more powerful model shifts your operating point slightly, but does not remove the bottleneck. The exploration architecture itself needs to change.
Let me play devil's advocate one more time, though. The benchmark only includes issues that at least 2 successful agents solved. So by definition, it is selecting for easier issues. Is this actually representative of real-world software engineering?
That is a genuine and important limitation that the researchers acknowledge directly. Because SWE-Explore only includes issues where multiple agents succeeded, it does not represent the full distribution of hard or unsolved problems. The harder issues in the dataset show much flatter response curves, meaning even perfect exploration does not help much when the issue is fundamentally beyond the current agent's ability to fix. The benchmark is designed to measure exploration quality in cases where exploration is the bottleneck, not to claim it captures all of software engineering. The trajectory-derived ground truth is also an empirical approximation, not a proof that other evidence could not support a valid solution. These are real caveats, and the authors are transparent about them.
So what does this all mean practically? If I am building an AI coding tool, or I am a researcher working on these systems, what should I take away from this?
A few things. First, the pass-fail resolve rate that the entire field benchmarks against is hiding important information. Two agents can have very similar overall resolve rates but completely different exploration profiles, and understanding that difference could point toward very different improvements. Second, the research shows that the key bottleneck right now is line-level recall. Agents need to find more of the specific evidence, not just the right general area. Third, the iterative code graph search approach used by CoSIL is a strong signal that the exploration strategy matters more than the underlying model size. And fourth, the finding that missing core evidence hurts much more than redundant context means that conservative, high-precision strategies that filter aggressively are probably the wrong direction. You want agents that read more broadly and surface more of the critical evidence, even if some of what they surface is not perfectly on target.
And I think the broader point here is that AI systems can look very capable on a course metric, while quietly failing at a crucial intermediate step that nobody thought to measure. SWE-Explore is a reminder that decomposing the problem and measuring each piece separately can reveal things that end-to-end metrics completely hide. That is actually a lesson that goes well beyond coding agents.
That is a great way to put it. And the benchmark itself is publicly available along with all the code and data, which means anyone building the next generation of coding agents has a concrete, rigorous target to shoot for. Not just can your agent fix bugs, but can it actually read the right code before it tries? That shift in focus could genuinely change what progress looks like in this field over the next few years.
And that is a wrap for today's episode. If you found this conversation valuable, consider subscribing and turning on notifications. We release new research breakdowns regularly, helping you stay on top of the latest discoveries without having to read every paper yourself. Thanks for listening, and we will see you in the next one. Goodbye.